Hi everyone. Today we're going to learn about survival analysis in Stata. Now survival analysis is something a little different than we've seen in the past. In survival analysis, we're concerned with analyzing times, that is time to event data. We could examine the time to death, time to MI, time to relapse, and so on and so forth. And so our goals for this tutorial will be 1. Estimate the survival function, and 2. To compare the survival function between two groups. So for this tutorial, we're going to use data from the Digitalis investigation group. And just to refresh your memory, the DIG trial was a randomized, double-blind, multi-center trial designed to examine the safety and efficacy of digoxin in treating patients with congestive heart failure. And so patients were randomized to either see the treatment or the placebo. And we are interested in comparing overall survival between the two groups. So the data set is located below and it's called dig.dta. Now please use this data set for the lab as opposed to another dig.dta, as this data set is a random sample of 1,000 patients from the original data set. So there's only 1,000 patients in this data set. So be sure you're using the correct data set. So if you would now open the dig.dta dataset in Stata below. Now before we can begin analyzing things, we need to tell Stata that we are working with survival data. And this is analogous to how we had to tell Stata that we were working with survey data when you were analyzing survey data. So we have to do the same thing for survival data. So the command for survival data is stset, one word. Then we have to put our time variable, our time to event variable, which for this example is death day, one word, comma, failure, open parentheses. And then we need to put our censoring indicator, which is death here. And we have to know which value corresponds to a failure. So the value 1 corresponds to a failure. Now hit enter. Now what this command does is it tells Stata, it says, hey, Stata, I have survival data, stset, and my time variable is death day, and death is my censoring indicator, where a value of 1 is a failure. Now Stata will, after you run this command, Stata will print out some descriptive statistics that you can browse at your leisure. Now the first thing we want to do is we want to estimate the survival function for the two groups. So with no missing data, i.e. no censored observations, this is easy. So for example, if we just want to estimate the probability of surviving beyond 1 year, we take the number of people that survive beyond 1 year and divide it by the total number of people in our sample. It's just a simple proportion. And that's easy. That's easy to do, and it's easy because we don't have any missing data. We don't have any censored observations. But estimating the survival function is more difficult when we have censored observations. Because remember, for censored observations, we only know that this person survived beyond a certain time. We don't know their exact failure time. We don't know the exact time that they died. So all we know is that they survived beyond a certain point. So this is a form of missing data. And so Kaplan and Meyer came up with a remedy for this problem. And now we're able to estimate the survival function, and it's called the Kaplan-Meier estimator of the survival function. So let's go back to Stata. Now the command to estimate the survival function, it's sts graph. Since we want to do it by treatment, we have to put comma, by, and then treatment, trtmt. So the Kaplan-Meier survival estimates will appear. And just from eyeballing this, it appears that the treatment doesn't have an effect on overall survival. I mean, the two curves are basically overlapping one another. Now in the New England Journal paper, which is below, it's labeled NEJM_dig, The authors plotted 1 minus the survival curve, and that's in figure 1. And so how do we do this in Stata? We want to graph 1 minus the survival curve. Well, it's very easy. Once again, we type in STS graph, comma, then we just have to add in failure as an option, and then again by treatment. And the Kaplan-Meier estimates appear. Now this is 1 minus the survival curve. Now keep in mind that this figure isn't going to look like figure 1 in the New England Journal paper. That's because in the New England Journal paper they used all 6,800 observations, and we only used 1,000 observations here. But if you look at the two, they look very similar. So now we want to move on to hypothesis testing. And to do that, we're going to use the log rank test. And that's used to test whether two survival curves are equal. Now this test uses the Mansell-Haensel test statistic. Essentially what it does is it creates 2x2 tables for each time t at which a death occurs. And so let's see how that's done in Stata. So the command for the log rank test is STS test treatment TRTMT, comma, log rank. And our null hypothesis for this test is what? It's that the two groups have the same distribution of survival times. So the two groups have same distribution of survival times. And the alternative is that they do not. So Stata will give us the value of our test statistic right here. In this case it's 0.00, and our p-value is 0.96. So now if we did the log rank test at the 0.05 level of significance, we would fail to reject the null hypothesis. Our p-value is 0.9616, which is greater than 0.05. Remember that our test statistic under the null has a chi-squared distribution with 1 degree of freedom. Now if you look in the paper, in the New England Journal paper, they use all 6,800 observations, and they get a p-value of 0.8013. And that's reported in figure 1. So using 1,000 observations, we reach the same conclusion as the paper, and that is we fail to reject the null hypothesis. And thus we conclude we do not have evidence that the distribution of survival times is different between the treatment and placebo groups. Now the last thing I want to mention is the concept of regression in survival analysis. So there is this concept of regression in survival analysis, and I'm sure most of you have probably heard of Cox's proportional hazards model. And so what most people do is they don't model the survival function, they'll model the hazard function, and they'll do that using a Cox's proportional hazards model. Now these concepts are outside the scope of this class, but I would be committing biostatistics malpractice if I didn't at least mention them. Other than the Cox proportional hazards model, again, there's many other models do exist, but as I mentioned, they're outside the scope of this class.